Hey everyone, welcome to the first video for section 3.7. So we're jumping ahead to 3.7 here in order to take what we did in the last 4 sections about solving constant coefficient homogeneous equations and apply that to some sort of physical situation. So for this section, we'll be looking at mass on a spring and write an equation for that physical system, which turns out to be a second order linear constant coefficient homogeneous ODE. So in this section, we're looking at that problem in particular, and we'll look at solving it and all the different cases that come out depending on what the damping coefficient is, the different kind of results you get. So let's go ahead, and this video is just going to describe and define the equation that we're going to be looking at for the rest of this section. Let's go ahead and jump on into it. So in this section, we're talking about the equations governing a mass on a spring. And the main thing that we're going to start putting this together is going to be Hooke's law, which basically says that the spring exerts a force proportional to the displacement of the mass along the spring. So the force applied by the spring is K times delta x, where delta x is how much you've moved the spring. So if it's all together, there's no force coming out of the spring, but as you start stretching it, it starts pulling back a little bit on the mass. So what this lets us say is if we were to take the mass, put it on the spring, and just kind of let it hang, there's a certain distance it would hang. So this means there is a distance L so that the mass times gravity, i.e. the force pulling down on the object, equals K times L, where K is this spring constant that comes from Hooke's law. So we're going to call L the equilibrium length, and then in deriving our equations, we're going to let U, which is going to be our unknown function, be the displacement from the equilibrium length. So I'm going to draw my picture here again. And let's look at trying to derive an equation for this. So first of all, we're going to use Newton's laws in general for how this works. So mass times the acceleration, which is the second derivative of u, equals a capital F of t, which is going to be the net force on the system. Well, what is the net force on the object? What plays into the net force? Well, F of t has several different terms. A couple of which should be fairly obvious. So the first is gravity, which is going to be m times g. Yeah, and gravity here is positive because we're going to assume that the downward direction is positive. So if it's displaced positively, that means it's pulled further away from the equilibrium length. And if it's negatively, it's pushed up into the spring a little bit. So there's gravity. There's the spring force, which is going to be negative K times L plus U. Why? Because the total force exerted by the spring depends on the total length, not just the distance from equilibrium. So it should be K times L plus U in that term. And then we have a damping force or a resistive force, which is going to be in the spring, and it determines how much the spring loses energy as it expands and contracts. So it's not going to do it perfectly, it's going to lose energy somehow, so we're going to put that in here as a resistive force, which is going to be gamma times u prime, coming in with a negative sign because it's always going to oppose our motion. And finally, there could be a fourth component, which is going to be an applied force. Some applied force, which I'm just going to leave as F of t for now, and we can change it later and make it whatever it needs to be. But these terms all factor into what happens in our equation. So let's take all this, put this on the F of t side, and see what happens. So I'm going to get m times u double prime equals what? Equals mg minus, and I'm going to distribute the spring force out, kl minus ku minus gamma u prime plus f of t. And now, because of the definition of L, our equilibrium length, we know that this and this turned into zero when you put them together. So if I rearrange this equation, I get mu double prime plus gamma u prime plus ku equals f of t, where m, gamma, and k are all positive constants, and f of t is some function, which I'm going to call the forcing function, and we'll talk about that a little bit later when we start doing things from here. So all of that work gets us to this equation right here, which if you look at, you'll see is second order, it's constant coefficient, and it's linear. So if the little f of t on the right-hand side was 0, all the methods we've done in this chapter so far would give us ways to solve these equations. And so the first thing we're going to do is look at when f is 0 and sort of derive our equations from there. So this, along with two initial conditions for the initial position and velocity of the mass in the spring, will let us completely define an equation that describes the motion of that mass over time. We can write down the equations, we can solve it out, and we can see what's going to happen to that mass over time. All right, that's the point I want to get to in this video. I'm going to put up a sample problem for you, which is just going to be translating a word problem into an equation. It should not be too difficult, but I'll put that up for you now. All right, so there's a problem for you guys to look at. Basically, you just have to put all the numbers in the right spots, write your ODE and your initial value, initial condition for this problem. I gave you a note there about units, so that the units I'm using for force are newtons, and newtons are kilogram meters per second squared, so make sure units work out on both sides of your equation. All right, that's it for this one. In the next one, we'll start looking at what actually happens to these solutions over time and what kind of things we can talk about in regards to what happens to the mass on a spring from the stuff we've talked about for the last couple of days. All right, thanks for watching, and I'll see you in that one.